Saxon Advanced Mathematics, lesson 106. Today we're going to talk about how to move an ellipse and a hyperbola off the origin. We've dealt with these shapes in the past, but always we've kept them centered perfectly on the origin. And today we're going to move them off. John has a much more boring name for this lesson. I'm not even going to tell you what it is, but I am going to enjoy it because it is an idea that we've danced around for a long time, and today we're going to deal with it. Now, we've dealt with moving a circle off the origin before. We know that this is the simple version of the equation of a circle. Okay, so this is what I'm going to call centered, meaning this is the equation that we use when the circle is centered on the origin. If we want to change it off the circle, this is how we do it. H and K are the modifiers, okay? And so this is how we write the equation for a circle. I better write centered at the origin here, because I'm going to write here centered on point HK. So H is the change on the y-axis, or the x-axis rather, sorry. It goes with the x-axis, and we notice that it's got an opposite sign. So if we want to change it 5 units to the right, which would be a positive 5 change, we write it as -5 here. So that seems kind of backwards, but whatever, we can deal. Same thing if we want to move it up 3 units, we would write -3 here. So the sign is backwards. I have a hard time remembering which goes with X, the H or the K, and which goes with Y, the H or the K. And here's how I remember it. I mean, besides alphabetical, which you'd think would be enough, but an X and a K look a lot alike. I don't want to put them together. A Y and an H look a lot alike. I don't want to put them together. So this strategy of using H and K to be the new center and to adjust our X and Y are exactly what we're going to do to adjust the equations of our ellipse. So let's look at that next. When we centered it on the origin, we wrote the equation like this. This is centered at the origin. And if we want to move it off the origin, we do the very same thing. Oh, I forgot to write =1. Sorry. This is centered on HK. Remember that the ellipse and the hyperbola look a lot alike. I'm going to show you the hyperbola in just a minute. Remember that with the ellipse, we're adding the 2. And then let's move on and let me show you the hyperbola before we get into the examples. Hyperbola. Centered on the origin, it was x squared over a squared minus y squared over b squared equals 1. Yeah, I should have that on every single one. I get so involved in writing this part that I forget the equals 1. This is centered at the origin. And then same thing, we use H for our horizontal change, opposite sign. This is over a squared. And then we subtract y minus k, quantity squared, for our b squared equals 1. And this is centered on point HK. k. All right? And remember, we just have to be careful about those minuses. Easy, right? So the other thing we want to talk about is, and I think I want to deal with this in the example. I don't think I want to explain it. We've got the general form and the standard form of the equation. The standard form is what I've been showing you here. This is the form that we use when we need to graph it, right? Because that is very useful for that. And we have done a lot of graphing. All right, the other form is called the general form. And that is useful for when we're trying to do algebra, to change up the numbers. The general form of any of these shapes can be written like this. It's a lot, right? But for almost all the conic sections we will study, for us, b equals 0. So we don't have this term. And now it looks more familiar. We have an x squared and a y squared, a plane x and a plane y, and then a number. So this is the form that we'll be using. This is useful for calculations. All right, so they both have a value. And in the examples today, we're going to practice going back and forth between them. There are only, there's just 2 examples. One will practice with a ellipse, and one will practice with a hyperbola. All right, so let's dive into that. Example 106.1. says, describe the ellipse 3x squared plus 2y squared we're going to graph it. Okay? John just says describe, which is more trouble than it's worth. We'll just graph it and that'll be easier. Now we can see kind of that what John has given us, oh, it's over here. What John has given us is basically the general form, right? He's given us x squared, x, y number. X squared, y squared, x, oh, I forgot the y. I mean, see how useful it is for me to check? 5, 0. Okay, beautiful. So that is what we've got. How do we turn this standard form, general form into the standard form? Because this is the one we want so that we can graph it. All right, so what do we do to take this general and shift him up? The first thing we do is rearrange the terms, because what we're going to be doing is completing squares. So we want to get the x's together and we want to get the y's together. So here are the x's. So I'm going to do 3x squared minus 6x, and I'm going to put those in a parenthesis, and then I'm going to write plus, and then I'm going to put 2y squared plus 8y with more room, and then I'm going to kick him to the curb. He's going over there. All right, now as I glance at these, I go, I don't like it. I don't like these lead numbers on the squared terms. But when I glance again, I see, oh, those can easily be factored out. So let's do that. 3x squared minus 2x plus 2y squared plus 4y. And that doesn't change anything, so we don't need to do anything to the minus 5, right? We're just factoring. We're not bringing any new numbers into the mix. All right, now we need to calculate these magic numbers. and figure out what to add in these two spots to make these perfect squares. That's what we're gunning for here. Magic number, we take the number in the B position, we divide it by 2, we square it, and that's what we add to both sides. What's inside of here is what we'll write in the parentheses when we write it as a perfect square. So for this one, we have minus 2 over 2 squared. That becomes minus 1, so this is plus 1. And then over here, we have 4 divided by 2 squared. I'm going to want these numbers later. This is plus 2. Plus 2, and then squared is 4. Now, we know that because we've added these numbers here, we need to add them over here as well. But we don't want to write plus 1 and plus 4, and let me tell you why. We added a 1 as the magic number for this, but we also have it within the parentheses that are being multiplied by 3. So we actually have to add 3 over there, right? Because that's 3 times 1. And similarly, we're not just adding 4, we're adding 2 times 4, so we have to add 8. Okay, right? We get it. So now we're ready to rewrite this as a perfect square. The outside factor still stays. This, I want this number on the inside, so it's x minus 1 quantity squared. Double check to make sure we completed that square correctly. This should multiply to that, yes, positive, and add to this, yes, minus 2. Plus 2 times, now this is a perfect square. This tells us the number that should go in there, y plus 2 quantity squared. Let's check to make sure we're right. This should be 4, and then when we add them, that should also be 4. Beautiful. Okay, and then over here on the right, what have we got cooking? This is 11 minus 5, so this is 6. All right, so we completed the squares. We factored out what we didn't want first, then we completed the squares. We balanced these magic numbers on the other side by remembering that this matters. And now our last step is we have to turn this into a 1. Thankfully, John set this up so that it's all going to be neat and clean. So this will become x minus 1 squared over 2 plus y plus 2 quantity squared over 3 equals 1. Now, how are we going to graph this? Because we remember that in order to graph the ellipse, this needs to be a square and this needs to be a square. Well, it is. These are perfect squares, just of weird numbers. So we can rewrite it one more time. The perfect square of this is square root of 2 squared. Let's put parentheses on just to keep it neat. So this value is square root of 2. When we square it, we get 2. That's weird, but kind of like deliciously obvious. This stays the same. And the number that you multiply by itself to get 3 is square root of 3. Okay, so this is now our original ellipse written in standard form. This is general form, this is standard form. Standard form helps us stand up and draw it. Okay, so now we're ready to do so. And we can see, oh look, there's our H and K, right? So the center, I'm just going to write it here where we can see it. The signs are opposite. So the center is 1 minus 2. All right, let's take that to the next page and let's draw our picture. We know that the center is 1 minus 2. We figured that out a hot second ago, right? There it is, right there. And then we know that our A value is square root of 2, and our B value is square root of 3, right? Because this is A squared and B squared. That's why we wrote them that way. Okay, now, here is the fun way to draw it. We just draw We're not going to go off the origin. We're just going to say, oh, look, this is the center, and it is point 1, negative 2. Now, how do we draw an ellipse? Well, we know that A is the value from the origin to one extreme. So this point, this dimension is square root of 2. I'm not defining this point because I would have to take this number and add square root of 2 to it. It would make an icky number. I don't want to do that. So the way I'm describing my ellipse is I'm just describing the length of the, in this case, it's the minor axis. And then up here, oh, I'm sorry, this shouldn't be an X, this should be a 2. And then this length is square root of 3, as is this, right? That's the major axis. I'm not trying to write what the points are because that's not easy to figure out. I would have to be adding and subtracting that weird root. I don't want to do that. So I describe my ellipse by defining the lengths of the axes rather than the points. I could if I wanted, couldn't I? I know that this, whatever, I'm not even going to talk about it, right? But we could do the calculations, but we don't have to. We just draw the picture. Oh my God, pretend it's perfect. This looks like a skull to me. All right, by describing these axes, that gives us plenty of information. We don't have to define the points. Okay, so that's our final answer. This is part of our answer. I guess I would say the whole thing, right? We used this information here as well as here. John gives us this answer. John did not draw a picture. He just said, this is the equation of an ellipse whose center is 1 minus 2. Yeah, we said that. Whose major axis is vertical of length 2 square root of 3. Now, is that what ours is? This is square root of 3 and this is square root of 3. So yeah, the total length here is 2 square root of 3's. And the minor horizontal axis is 2 square root of 2. And that's exactly what we show. 1, 2 of them, right? So we could say major axis equals 2 times the square root of 3, and the minor axis equals 2 square root of 2. We could come out and say that overtly if we wanted, and that would also be correct. All of this is correct. Yay, there's just smiley faces everywhere. Depending on what John wants to tell you, depending on how much information he's asking for, any or all of this information could be helpful. Okay, so this is how we take an ellipse off center. The next problem will take the hyperbola off center.